Hello everyone. Today I am excited to present our project on building a real-time EV dashboard and ADAS warning system. This project is a deep dive into embedded systems development using ARM Cortex M3 architecture via the STM32 microcontroller. Our goal specifically was to simulate the core electronic functionalities of a modern electric vehicle while focusing on real-time data acquisition including physics-based modeling and predictive safety features also. Throughout this presentation, we will look at how we integrate various hardware sensors and software logic to create a system that monitors vehicle health like speed, battery, life, SOC, etc. But whilst doing the driver assists avoiding collisions, etc. This project bridges the gap between academic theory and industrial application using tools and protocols that are standard in automotive world. So let's begin. The heart of this project is a dual module architecture consisting of an EV controller and an ADAS engine. The EV controller is responsible as it is brain of the vehicle, managing torque, calculating speed, and tracking the state of charge, or as we know it as SOC. The ADAS engine mainly focuses on safety, specifically, for example, obstacle detection, collision warnings, etc. Architecturally, we use STM32 as our electronic control unit, or famously known as ECU. It collects data from sensors like potentiometers, pedal, ultrasonic sensors, etc. that processes the data in real time using complex physics formulas and then streams the result via UART communication to a graphical Python dashboard. This structure mimics the real-time processing and telematics found in the high-end electric vehicles today. Further, the hardware overview. Our choice of hardware is the STM32F10 3C86, popularly known as the Blue Pill board. This board is powered by an ARM Cortex M3 core, a 32-bit RISC processor that is a staple in the embedded industry due to its low power consumption. Also, this has high performance. This operates at 72 megahertz. It provides the what we can say it has speed necessary for rapid calculations required is in an automotive environment. The board features 37 general purpose IO pins and 4 ports which we use to connect our array of sensors and indicators. Understanding this hardware is vital as it is ARM based controller like one power 95% of the modern smartphones and are the industry standard for automotive ECU and industrial automations as well. To develop our system, we utilize professional grade tools such as STM32 Cube IDE, which uses C language. We also leveraged the hardware abstraction layer, which provides built-in functions to easily manage complex peripherals like timers, communication ports. Because we are working in a simulated environment, we used Pixim Lab. This powerful simulator also allows us to verify our code on a virtual blue pill board, complete with a peripheral modules like potentiometers to simulate pedals and virtual LEDs for status indicators. This is also known as a host to target workflow, wherein we develop on a laptop and deploy to the microcontroller, which perfectly mirrors the development process used in the automotive and aerospace industries. While it may not be as effective as real world or practical environment, this is the closest we can get to. Further moving on, data acquisitions, vehicle inputs like throttle, brake positions are naturally analog, but microcontrollers can only process digital signals. We all know that. So in order to connect both of these analog and digital input and outputs, we use STM32 microcontroller. This has a 12-bit analog to digital controller. This peripheral samples voltages between 0 to 3.3 volt and converts into digital values 0 to 4095, as it is a 12-bit microcontroller, as it has 12-bit ADC. In our project, we use 4 potentiometers to simulate the physical sensors of the car. Uh, they are acceleration pedal, brake pedal, SOC, and the temperature of the motor. By reading these values, these digital values, as we simulate in our PixSim simulation, our software can precisely interpret the intent of the driver, uh, like how hard the accelerator is being pressed, or we can use the data to drive our physics models. Further moving on, obstacle detection via the ultrasonic sensors. For our ADAS module to see, we have integrated HCSR Not 4 ultrasonic sensor. Unlike light-based sensors, this uses sound waves to detect obstacles. The process begins with STM32 sending a 10 microsecond high pulse to the trigger pin. This sensor then emits an ultrasonic burst. Once the sound bounces off an object and returns the echo pin returns, the echo pin goes high. By using internal timers to measure exactly how long the echo pin stays high, we can calculate the distance to the obstacle. We use the physics formulas where the distance equals time multiplied by the speed of the sound divided by 2 for one way distance. Further moving on, the ADAS engine, predictive safety. The ADAS engine uses distance data to predict and prevent accidents. The core calculation where here is time to collision, or famously known as TTC, which is front distance divided by the vehicle's current speed. We have established safety thresholds to assist the driver. Warning: a warning is issued if the front distance is less than 50 centimeter or TTC is under 3 seconds. Critical alarm is triggered if those values drop to 20 centimeter or TTC goes up to 1.5 seconds. We also implement BST or blind spot detection if an object is detected on the left or right within 30 centimeter while the vehicle is moving at more than 20 kilometers per hour. The system activates specific warning LEDs to the alert to the driver, and hazards are also detected which they may not see through blind spot detection. Further moving on, EV controller and physics modeling. The EV controller manages the vehicle's performance using a physics-based inertia model. Rather than using a simple lookup tables, our system calculates acceleration and speed based on real-world factors like motor torque, vehicle mass, and aerodynamic drag. Torque is derived from the acceleration pedal position and is scaled according to the selected drive mode. As we know, there are many modes that are put into vehicles in today's era. The famously known are eco, normal, or sport. We also have implemented regenerative braking. When the driver presses the brake pedal, the software simulates a negative torque that recharges the battery instead of draining it. Finally, the controller estimates the vehicle's range, predicting how many more kilometers can be driven based on the current battery energy and also consumption rates. Moving on, to manage the vehicle's logic, we use finite state machines. These ensures these ensure that the vehicle only performs action appropriate for its current state. Uh, Also, they can be called as drive selectors or gear selectors, which are park, ready, driving, or regenerative. For example, if the motor won't start until in the ready state, preventing accidental acceleration. Complementing this is our fault management system, which constantly monitors for critical issues like motor overheating, dangerously low battery, or imminent collisions, which which driver may have not or is which the driver may have not detected, or he might have neglected it. If a fault is detected, the system registers a specific fault flag and transitions the vehicle to a fault state, immediately cutting the motor torque off for zero safety for full safety. Finally, UART and command shell for communication. The final piece of our project is communication layer using UART protocol, or the full form or the abbreviation is Universal Asynchronous Receiver and Transmitter. Here we use baud speed of 1,15,200 baud. This allows the our selected microcontroller to stream all the vehicle data to a Python dashboard for the user to see. We built a diagnostic command shell which allows for two-way communication using a terminal. A technician can send commands like status to get full system readout, or fault clear to reset the vehicle after a survey, or this shell can even also be used to inject test values like setting a specific speed or temperature to validate the system's response. This telematics capability is essential for modern vehicle maintenance and real-time monitoring. So yeah, uh, these are all the things that we have done in our internship, or these are all the things which I have learned from the internship. Further, nothing more else. I'm looking forward to many opportunities uh, through this internship. Thank you.